Hi, today I'm going to talk about classification and representation of rank 2 root systems. Now, we've seen some discussion of root systems in class, but mostly from the context of using them as a tool to classify Lie algebras. But here what I'll do instead is introduce them from scratch as a mathematical object in their own right. Okay, so we'll just start with the definition here. So a root system, which we'll denote phi equal to ER, is an inner product space, E, along with a subspace R in E, such that first, E is going to be spanned by R. Here, this second condition tells us that the only scalar multiples of our roots that are allowed are plus and minus 1. And this third condition, for any two roots, we have that there's this integer quantity. Here the angle brackets denote the inner product. So 2 times beta alpha over alpha alpha is going to be an integer quantity. Alternatively, you could define this as without the 2 and say it's an integer or half integer quantity, but this is better. And here, based on that quantity m, if we have two roots alpha, beta, and r, then sigma sub alpha of beta, which is going to be beta minus m times alpha, is going to stay in r. And here, this sigma alpha of beta is going to represent taking b and reflecting it over the line that's perpendicular to alpha. So I'll show that here. So if we start with this vector alpha, this vector beta, and try to find sigma sub alpha of beta, what we do first is we look at the line perpendicular to alpha, and then we're going to reflect beta over that line. So that's the output of sigma alpha beta. So the idea is that if these are roots, then this is also a root. Okay. We also say that a root system phi is of rank n, if and only if the dimension of its inner product space is n. Okay, so now that we have that basic definition of a root system, we can try to look at those conditions and see where those restrictions lead us when we're trying to actually construct our root systems. So we start with this proposition here that says if alpha and beta are roots of a common root system, and if we assume alpha is not a multiple of beta, and suppose alpha alpha is bigger than beta beta, so this would tell you something about the magnitude of the vector, then one of the following holds. So first is that alpha beta is 0, and the angle between them is pi over 2, so there's orthogonal vectors. Next, you have that alpha alpha equals beta beta, and the angle between them is going to be either pi over 3 or 2 pi over 3. Next, you have alpha alpha equals 2 times beta beta, and the angle between them is pi over 4 or 3 pi over 4. And lastly, the same thing, but 3 beta beta. And the angle between alpha and beta will be pi over 6 or 5 pi over 6. So over here, we have the angles between. So in terms of our restrictions, we have our angles here. This is what they'll fall into, one of these 4 categories. And here, this tells us about the length of the vectors. So here, the lengths are the same. And here, they'll differ by a factor of what will end up being a factor of root 2, and here root 3. In the first case, we don't have any restriction on the lengths. Okay, so we'll actually go through the proof of that proposition now. So if we take alpha and beta to be any two roots of the root system phi, where alpha is, again, not a multiple of beta, and we suppose alpha alpha is bigger than beta beta, and then by property 3 of the definition of root systems, we have these two integer values here, m and k, as defined in the definition, and those are all going to be integers. They're both going to be integers. And because they're integers, we can multiply them together to get another integer. So here we'll have 4, so 2 times 2, and then this whole mess. And then by the definition of, by the linear algebra definition of cosine, we have this equality here. So we have that mk is 4 cos squared of theta, where theta is going to be the angle between alpha and beta. Okay, so we rewrite that here. And because we know mk is an integer, and we know the restrictions we get from cosine squared of theta, we know that mk will lie somewhere between 0 and 4. So it will be either 0, 1, 2, 3, or 4. So if mk is 4, what we'll find is that we're going to be able to discard this case, because if mk is 4, then we have that cosine squared theta equals 1. So because theta will be somewhere between 0 and pi, theta will have to be 0. So then that means that alpha is a multiple of beta, and we assume that to be not true. So we can discard that case. For the remaining cases, if mk is 0, then we have that 0 equals cosine squared of theta. Again, because theta is between 0 and pi, we have theta is pi over 2. And so alpha and beta are orthogonal. Okay, if mk is 1, then cosine squared theta equals 1/4. So we'll get that theta is pi over 3, or theta is 2 pi over 3. And here, because m times k equals 1, and m and k are both integers, we know that they're both going to have to be plus or minus 1, where they'll have the same sign. So we have that m equals k, and we can rewrite that as this, and rearranging this, we get the equality we're looking for, that they have the same magnitude. Okay, and similarly for mk equals 2, cosine squared theta equals half, so theta equals pi over 4, or theta equals 3 pi over 4. And here again, one of mk is plus minus 2, and the other is plus minus 1, and again we have a matching with the sign. And here we say 2m equals k, and the reason I assign 2, I assign the 2 to this one and the 1 to this one is because we assumed that the magnitude of alpha was bigger than the magnitude of beta. So that has to be that way. So we rewrite this way and rearrange to get this. And exactly the same for 3. We get that theta is pi over 6, or 5 pi over 6. And we arrive to the same conclusion, that alpha alpha equals 3 beta beta. Okay, so that's how we generated our 4 cases. Okay, so as we move on, given that proposition, we're going to need the notion of root system isomorphism. So given two root systems, phi equal to ER and psi equal to Fs, and a bijective linear transformation T between them, such that T of sigma sub alpha of beta equals sigma sub T of alpha of T of beta. But really it's just that this action of sigma alpha can come out of the linear transformation in this special way for all of our roots. So if that's the case, we say that phi is isomorphic to psi, and we denote this in the usual way, and then we would also say that T is an isomorphism. Okay, so now we're going to try to show things, what the systems of rank 2 look like, but I think it makes sense to start with what the systems of rank 1 look like. So it turns out that up to that notion of isomorphism that we just discussed, there's only actually one possible system of rank 1. So the idea is that if we start with any root in R, since E is of dimension 1, so it's a rank 1 system, so E is of dimension 1, no matter what alpha is, we're going to be able to span E with just that vector. So the only other root is going to be minus alpha, because we're on this line here, so we can't do a scalar multiple of alpha that lies somewhere down here, because that's not allowed. You're only allowed to have plus minus alpha, so that only allows us to have minus alpha over here as our other root. We could rescale this system, but that's why it's going to be up to isomorphism. And we can see that this is consistent with our sigma alpha action as well, because if we imagine the line perpendicular to alpha that goes through the origin right here, reflecting minus alpha over that line would just take you straight back to alpha, and the other way around, if you imagine reflecting alpha, it would go back onto minus alpha. So that works out nicely. Yeah. Okay, so systems of rank 2 are going to all look, there's going to be 4 of them, and I'm going to go through them each here. So the first one we have is A1 cross A1, and that previous system we had is what you would denote A1. So here, your first possible system is just going to be 2 copies of A1. And here, these are going to be at our pi over 2, our angle of pi over 2 away from each other, so this will be our first case. And I'll also note here that the lengths of these 2 vectors don't have to be related at all. They're independent of each other. So here you'd have like alpha and minus alpha, and this would be beta and minus beta. but other than that, they're unrelated. Okay, then we move on to our A2 case, where we can see there's 6 sections here. So this is going to be our pi over 3, the one that corresponds to our pi over 3 case, and these are all going to be of equal length. Okay, and then we have the next two, B2, which is going to be our pi over 4 case. So we have 8 vectors here, pi over 4 apart. And then the lengths here are going to differ by a factor of root 2 every time you go to the next one. And similarly for G2, we have 12 roots. Here they're all separated by an angle of pi over 6. And the lengths here are going to differ by a factor of root 3 as you go around. Okay. So based on that, we'll get our theorem. So every rank 2 root system is going to be isomorphic to one of those above systems, one of those 4 above systems. Okay, so we'll run through the proof, and it's going to basically just follow from our proposition eventually. So let's take phi equal to ER be a rank 2 root system, and we'll let theta be the smallest angle between any 2 roots in R. Okay, so since the dimension of E is 2 and R spans E, there's going to exist 2 roots, alpha and beta, that are linearly independent. Otherwise, we wouldn't be able to span E. Okay, so if the angle between alpha and beta is bigger than pi over 2, well, then the angle between alpha and minus beta, which is also a root, will be less than pi over 2. So the smallest angle is going to have to be less than pi over 2. So that's nice. And we remember from our proposition that theta can only take 8 possible values. But now that we've restricted it to being less than pi over 2, there's only these 4 possibilities: pi over 2, pi over 3, pi over 4, and pi over 6. Okay. So now we're going to consider a new pair of roots, alpha and beta, such that alpha and beta are theta apart. Remember, theta is the minimum angle, so there's going to have to exist 2 roots that satisfy this. Okay, so the argument continues like this. We look at this object here. So sigma sub beta of alpha. So we know this is going to be a root. And then minus 1 times any root is also a root. So this will be a root. And we're going to look at a little geometric argument to say that this will be at an angle 2 times theta from alpha, at an angle of 2 theta from alpha and theta from beta. So this diagram is helpful. So sigma beta of alpha, when we reflect over that line, you're going to end up somewhere down here. And then taking the negative of that, you're going to jump up this way. We'll see that this angle here is actually 2 theta. Okay, and we can actually define a process like this where we sort of iteratively jump over the new roots we create. So if we reflect alpha over this new line, we'll create a new root that's at an angle 3 times theta from alpha. And we can continue that idea over and over again until you generate a sequence of roots which are integer multiples of theta away from alpha. Okay, but we can see that any value of theta evenly divides 2 pi into 4, 6, 8, or 12 roots. Okay, so what that means is that we're going to, as we generate those integer multiples of theta, we're going to wrap around. Okay, so we're going to suppose that there exists some other root gamma not generated by this process. So we've generated a bunch of these roots, but we just need to see that those are the only roots. So if there's some other root gamma, then it's either going to be a scalar multiple of an existing root, or it will be somehow independent of our roots alpha and beta, and exists somewhere in between the generated roots. First case is not possible because C is only allowed to equal plus minus 1. For the second case, if gamma did exist somewhere between the 2 generated roots, well, then it must be at an angle less than theta, which is not possible because we define theta to be the smallest angle. So we can see here, if we somehow had a gamma in between beta and alpha here, well, then the angle between gamma and beta would be less than theta, and the other way too. So that's not allowed. So such a gamma can't exist. And then from there, the lengths between these roots will correspond with the lengths outlined in the proposition, and the proof would look exactly the same as it did there. Okay, so here they are again. So these are our 4 possibilities. Cool. So now that we have our possible root systems, we're going to talk about different ways of representing them. So first we're going to talk about the Weyl group, and then we're going to talk about the Dynkin diagram. Okay, so for the Weyl group, if phi is a root system, we'll define the Weyl group W of R as the subgroup of the orthogonal group of E generated by the reflection sigma sub alpha for all of our roots. Okay, and we'll note that we can get to any root by applying these reflections, because we see down here applying the same reflection twice to a root brings you back. Okay, and then we have the following two propositions, and I give the outlines of these in my paper. So if phi is a rank 2 root system with a minimum angle theta equals 2 pi over n, then its Weyl group is isomorphic to the symmetry group of a regular n over 2 gon, or the dihedral group. Okay. And then next we'll need to define the definition of a base. So given a root system phi equal E of R, a subset delta of R is a base if delta is a basis for E as an inner product space, and each root of R is expressible by either a positive integer or negative integer, a strictly positive or negative integer linear combination of elements of delta. And it's also important that a rank n root system will have a base consisting of n roots. Okay, and then from there we get this proposition that any two bases, delta 1 and delta 2 of a root system ER, there exists a unique W in our Weyl group such that W acting on delta 1 is delta 2. Okay, and now we'll move on to Dynkin diagrams. So if phi is E of R, if phi equal to E of R is a rank 2 root system with base delta equal alpha beta, the Dynkin diagram for phi will be a directed multigraph on the vertices v1, v2. So we add 0, 1, 2, or 3 edges between b1 and b2, depending on if theta, the angle between alpha and beta, is pi over 2, 2 pi over 3, 3 pi over 4, or 5 pi over 6, respectively. And additionally, we'll add an arrow over the edges if alpha is longer than beta, basically. And we leave the edges unmarked otherwise. So we can see here the Dynkin diagrams for our rank 2 systems. So here our first one, A1 cross A1, we see that they're disconnected because they're at an angle, both of our roots are at an angle pi over 2 from each other, and no arrows, obviously. Okay, and then A2, we have one connection because they're at an angle of pi over 3 from each other, and no arrow because they're all of equal length. And here, we increase the number of edges for the decreased angle, and then we add the edge because there's a multiple of root 2 difference. And here we have the arrow again because of the multiple of root 3 difference and the decreased angle again for G2. Okay, and then from there we have one final proposition that a root system is irreducible if and only if its associated Dynkin diagram is connected. So immediately that would tell you that the only irreducible one we have here is, the only reducible one we have is A1 cross A1. Okay, so now for some concluding remarks. We saw that for all rank 2 root systems, we may reduce them to just 4 possible cases up to isomorphism. We saw that those cases were labeled A1 cross A1, A2, B2, and G2. And anyone familiar with Lie algebras would notice that those labels correspond exactly to the standard names for the families of the simple finite dimensional complex Lie algebras, as well as the name of the exceptional group G2. And from there, you would correctly guess that if you continued into rank 3 systems, you would find the same correspondence. So you would go up to A3, B3, and then C3. And yeah, I can show you here, there's a one rank 3 system. So this is actually A3, and this looks a lot like A2 because we have our vectors of equal length and the same angle between all of them. And then we can go eventually up to even higher dimensions, and we can see this familiar picture from our course on cue thumbnail, which is actually E8. So this is a rank 8 root system projected onto a plane, and this has something like 240 roots. Yeah, I thought that was a cool picture, but that's all I have for today. Thank you.